think that gentleman asked a very good question, and I will repeat that question again. You said that after using the resilient wheel, the contact force will reduce, right?
Yeah.
So you see, if you reduce the contact force, can you expect you will also reduce the corrugation? I mean the growth rate of the corrugation. Is that possible?
It's hard to say. In this presentation, we just think the corrugation is occurred, is there, and if the rigid wire loading connector, the evaluation is very high. If we change the rigid wire with the resistant wire, so the evaluation will be decreased. We just want to see this. And if we say that the dynamic force can reduce the rate of the corrugation, depending to maybe to be further investigated.
Okay, other questions, please? Another one, please, from the same man.
Okay, I will add another one. On your slides on the page 11, I noticed that you provide a formula saying that the frequency of the isolation equal to the square root of 2 multiplied with the frequency of that dynamic structure. So I want to know how that the coefficient. The coefficient is the square root of 2. How did you get this formula?
Okay. This is just the vibration isolation, the formula. It's very traditional. We can see it in some books. Yeah.
Question for Paul. Pretty exciting work. I'm really impressed. But as a practical friction modifier person who's seen a lot of sites, I would certainly agree that control of squeal is inconsistent on freight wagons. And I think the work in Australia with showing the very high angle of attack of some bogies or wheel sets is a strong hint as to why that might be. But my experience is that on metros and trams, the control of squeal is, in practical terms, is much more consistent. Right. And would your models predict that difference in consistency between some types of rolling stock to others?
I think the short answer is I don't know yet. The model can be used quite easily to investigate a range of different traffic, but you would need like a multi-body dynamics simulation of that different traffic and work out the lateral creep curves and the angles of attack, and then we could investigate the effects of different models. I know, freight, for instance, our experience with Queensland Rail was that freight trains tend not to corner very well, and they get very high angles of attack. The friction bowl may not be lubricated well, and that can have a big effect on squeal. Yeah.
Thank you. On the back. No other questions? Oh, sorry.
Thank you for the presentation. Also for you, Mr. Megan. I have seen that there was quite a big difference in your models regarding the friction modifiers used for testing. Could this be related to the amount of product used or something like this? Or how do you estimate the amount of product used? Because, I mean, in the water-based friction modifiers, the reduction was much less than in the oil-based friction modifier. So can be related to the product itself, or I don't know?
sort of feel like there's other experts here that could probably answer that. Yet the water-based, as I understand, the mechanism is quite different to the oil-based friction modifiers. My understanding is the water-based, you try and keep a nice intermediate level of friction, whereas the oil-based tends to lower the friction quite a lot. But I don't know whether, Don, you want to jump in, or is that okay?
Other questions? I have one for Paul. Squeal normally happens in sharp curves negotiated at normally low speed, so in shunting yards or in cities, so where normally full traction is not needed, so we are not on steep slopes or something like that. So do you think that using, we were used to call them high positive friction modifiers. So do you think that high is too high in this case? So should you use something that is less, that gives less friction, because I've seen that the curve is pretty high. And so although if you don't have any negative slope, but squeal happens as well. So using something that has a lower friction, so something more liquid, I don't know, or mimicking rain or whatever. Maybe this is a question for these guys. But
Yeah, I feel we haven't done enough investigation with this model. This is just research we've only just come out with, so we haven't had the chance to really investigate a range of different applications, as you're saying. Basically, all we've shown is that you can get squeal still occurring even though you have that positive slope quasi-statically. The induction, we're using that measured slope and then a well-established creep curve for squeal that has been validated on squeal measurements. And we're just modifying that non-rolling friction coefficient under quasi-static conditions, but the behaviour of the creep curve is still following the instantaneous. So I think the answer to your question is we haven't got the technology now to measure the instantaneous creep curve, because we're talking about things happening over 1,000 hertz. So we need something very fast to measure what's happening with the creep. So hopefully maybe in a year's time I could give a better answer.
Okay, other questions? Yeah.
So of course you can control squeal by spraying water on the rail, but people who've done it usually find it doesn't do very good things with the track or the rail. And while it's true that some sites with squeal are not under traction, usually metro systems do require their trains to stop in a predictable way, and using oil materials on the head of the rail is a bit potential to compromise that.
Maybe I have a question for you, if there are no other questions from the audience. You have used a model with springs and dampers. Dampers, okay.
Yeah.
This is a linear model, while the behavior of rubber is non-linear, for example, using the Mooney-Rivlin description of damping inside rubber. Do you expect to see different results by using constitutive models of rubber that are much closer to reality than simple linear models?
It's a very key problem. In the model, we just use the linear model of the rubber. We make a simulation. We think the resistance we are rolling on the track, the dynamic, the rubber pressed just in the linear rhythm. And if the rubber, we think if the rubber from we should, if the rubber consider of the frequency, or we can make the model more accurate. Yeah. But the main characteristics of the layer on the high frequency, I think this model can reflect the main advantage of the resistant wear. Also, whether the external or can consider the mooring model of the rubber. And the test of the rubber, and the parameters, we should do some test. And we can further do this work.
2 minutes left. More question from the back there.
I have a question to you, Mihan. Do you have experience, or do you know how long this friction modifier is effective in a curve, for example? How long curves distance is possible?
That's definitely
okay.
one
That's
for
maybe
these guys.
okay.
In my experience, for curve squeal, you can apply to treat 1 or 2 curves, maybe 200 meter distance maximum. About 200, yeah, roughly. Depends on curvature, length of curves, vehicles, etc.
Sorry if I add something, but I gave a paper on this in Brisbane in 2006, and we discovered that the friction modifier was effective for a much longer distance, for more than 1 kilometer, but it was not...
It was not curve squeal.
It's not curve squeal, it was railway, but it was effective for a very long distance. Sorry.
So I should add exactly what Andrea said. It depends on the functional target you have. It's different for corrugation, different for lateral forces, different for curve squeal.
Gentlemen, I was advised that the bus is waiting for us outside, so I thank again the authors, but we have to stop the session here.